To work with abstract algebraic concepts, we want to be able to use algebra tiles. And algebra tiles are just a way of representing these abstract ideas with a picture. To use algebra tiles, we need to first define what the algebra tiles are. Now, there's lots of ways to define them, but as long as you're consistent with your positives and negatives, whether you shade or don't shade, that's going to be what I'll be looking for. The textbook, I think, uses a red algebra tile for the little square for +1, but we'll just use shaded for positive and unshaded for negative. So the little squares represent 1, +1, and -1. The big squares are going to be positive x squared and negative x squared. And it's important to understand that these algebra tiles represent area. So this 1 represents an area of 1. That means then that it has a length of 1 and a width of 1. Here has a length of 1 and a width of 1 as well. So when we look at an x squared tile, we get a square that's made from a side length of x and a side length of x. So this area, the x squared, represents the area. So when we look at these x tiles represent area. So this represents +1 and has an edge length of x, and it matches the edge length of x on the x squared tiles, and it has the other edge length of 1 because x times 1 gives us 1, and this edge length will match the edge length of the 1's tiles. And when we actually have the physical algebra tiles, you'll see that they physically will match up. What you'll also notice is that no matter how many 1's you put along the x length, the 1's will never match up to the x length because we do not want to misinterpret this length of x as some number that we can actually calculate. Okay, this x represents some general unknown length of x. So again, just as long as you keep track of your algebra tiles as, shaded as positive and unshaded as negative, even if you flip it around and say that the shaded is negative and the unshaded is positive, that's fine as long as you keep it consistent, as long as you don't mix the shading and not shading somewhere in the middle of a problem. So we're going to use a green shaded for positive and the white for negative, and we're going to show what the algebra tile representation of this algebraic expression looks like. So this algebraic expression is 2x squared minus 2. Now, to be able to show this, we want to first of all make sure we have the right piece. We're going to use the squares, x squares, so we're going to use a big square. And we're going to shade that, so that's going to be 1x squared. And since we have 2x squareds, we need to show 2 of those. To show the -1 tile, -2, we show 2 -1 tiles. So we're just going to show 2 tiles that are white. So there is 2x squareds and 2 -1's, or in other words, 2x squared minus 2. For the -x squared tile here, we're going to just use a large square white tile. For the 3x, we have to make sure that the 3x has a different shape, and we're going to use the shaded as positive. And for the -2, we'll just use that as 2 white square tiles, the small square tiles. 2x squared plus 3x. Identify the parts that you have. X squared and x are different, so we need 2 different tiles for that. We're going to have a shaded x squared tile, so the large tile represents x squared. So we're going to have 2 of those. And we need to have positive 3x tiles, so I'm going to have shaded tiles for positive. And I'll have 3 x tiles. And when we draw this, notice that my edge length of x matches my edge length of x. And the x squared represents the area of that tile. The x represents the area of that tile. And you'll notice that some of these actually can be shown in a rectangular arrangement. So this is not something that we're going to focus on too much, but this is something that we start looking at a little bit later on, and that we want to know which one of these expressions can be shown in a rectangular arrangement. And if they can be shown in a rectangle, then we know that these are factorable expressions. Looking at D, we have 2 x squared tiles and 3 ones tiles. Now, this will not be able to be shown in a rectangle because we don't have anything that can match the edge lengths of these ones here. These x squared's edge lengths cannot be matched with the ones edge length, so this cannot be arranged in a rectangle. So this is an expression that we call is not factorable. If it can't be shown with length and width as 2 multiplying parts of length times width, or in other words, put it in a rectangular shape, we say that that expression is not factorable.